Hello again, everyone. We are back with Project 4. Of course, you know what materials we have from the last projects. We have gold tin alloy and copper oxide. Now let's get into the electron configurations of each element. So let's first say what an electron configuration is. This is a way to write out what energy levels around the nucleus the electrons are naturally in, and can be done using the diagonal rule, where you fill energy levels in accordance to this diagram until you have used all of the electrons around the atom. And this can be abbreviated by using noble gases to summarize the first chunk of the electron configuration by just saying that it is equal to that noble gas. And here you see all of our elements with their abbreviations listed below their standard electron configurations. You see that the only thing outside of the noble gas is what's left over and attached to the end here, and makes it much quicker and easier to write. Now let's talk about the band gap of copper oxide. First off, the band gap is the distance, or energy distance I suppose, between the valence and conduction bands of the electron levels. The copper oxide range for the band gap is between 1.2 and 2.5 electron volts, typically about 1.4 electron volts. But now, let's talk about doping for copper oxide. So copper oxide is an intrinsic p-type semiconductor, which means that it naturally conducts via holes, i.e. positive charges, and not free electrons. So naturally this makes p-type doping very easy and n-type quite difficult. N-type doping has been achieved in labs, but it isn't really useful for any sort of industrial purposes. So we'll talk about what elements are good for p-type instead. So both sodium and lithium are effective dopants, which means they increase the electron mobility in the semiconductor by adding more free charges. Now let's talk about mobilities, concentrations, and electrical conductivities of free electrons and holes in copper oxide. So of course, because it is a p-type semiconductor, the mobility of free electrons adds very little to the overall electron mobility. Most of it is the holes, the positive charges, that, as you can see, is order of magnitudes higher than what is added by the free electrons. So now let's talk about applications of copper oxide. So copper oxide, it's primarily used for solar cells, as you can see here. It is, with a number of other materials, used to construct solar cells. Well, thank you for watching our presentation.